Hi everyone, my name is Sebastian. I'm an assistant professor of electronics engineering at Sweden University, and today I would like to introduce you to our paper entitled A Distributed Measurement of Light Conditions for Indoor Photovoltaic Applications, which I've been working on together with my colleagues Xinyu and Bengt. So the background of this work lies in the field of energy harvesting, and more particular photovoltaic energy harvesting for indoor ambient light. An energy harvesting system typically consists of these parts that you see in the top of the slide, of an ambient energy source, in this case ambient light, an energy transducer, typically a photovoltaic cell or photovoltaic panel, a power management circuitry to adjust the output of the solar panel, and a load system, typically a low power electronic system such as a sensor system or similar. There are some applications, of course, that you might already be familiar with of this type of system. So all of you probably know these solar powered pocket calculators, or there are these wireless keyboards that are powered by photovoltaics, or a number of sensors, for example, in building automation. And the motivation of this is, of course, that these devices can get rid of the batteries and instead get a longer lifetime extracting energy from their environment. From earlier work, we know that there are different effects of the light conditions on the PV output power. And particularly, there are two things that determine the output power of photovoltaic systems, photovoltaic cells, which on the one hand is the light spectrum of the light source that is used, and on the other side, the spectral response of the photovoltaic technology that we apply. So here on the right hand side, you have an example. You have two different light spectrums from two different light sources. The red one is limited to the human visible spectrum, and the blue one is a wider spectrum that also includes some infrared components. If we then use a photovoltaic panel, in this case a crystalline silicon panel, which is sensitive also in the IV range, we can see that this results into quite significant differences in the output power that these panels produce. With a blue panel, or the blue spectrum here, containing infrared light, producing approximately double as much power at the maximum power point as the other panel. So from this, we can of course conclude that we need to characterize, or we need to include spectrum components in addition to the light intensity if we want to use the information later on to predict power. So to summarize then the aims of the study, on the one hand side, we want to propose a concept for distributed light measurements involving spectral information. We want to design a node prototype that collects these limited spectral informations in an efficient manner. And of course, we want to conduct an initial evaluation of the system and the data that we have collected. The system concept itself is pretty straightforward. It follows a standard traditional wireless sensor network kind of architecture, where we have a number of nodes distributed over different locations and places that we want to characterize light conditions in. And each of these nodes then wirelessly communicates the data that it collects to a number of gateways, which then forward the data to some sort of central database where users can access the collected data. I will come back to the technologies, but already to mention here, we're using lower WAN wireless communication for the nodes. So each node can directly communicate with gateways, and we do not need some sort of mesh type of topology. A little bit more specific, maybe the node design in our system. Here you can see the outside of one of the nodes that we developed, showing the parameters that we are collecting. Of course, since we want to monitor light conditions, we have ambient light sensors. Here on the bottom left, we have an ambient light sensor, basically measuring the intensity of the ambient light, or the lux level. A little bit particular about the sensor is that it has two channels, so we can get information both about the content in the human visible spectrum, but also the IR contribution from the sensor. In addition, we have a second light sensor, an RGB sensor, just limited to the human visible spectrum, but basically providing us more detail about this part of the spectrum separated into red, green, and blue channels. Then we also measure some reference conditions such as temperature, as well as the output or the influence the light condition will have on the photovoltaic panels. So we have included two photovoltaic panels here, a amorphous photovoltaic panel and the crystalline panel, and we measure their output by measuring the short circuit current of these panels using these current sense amplifiers. To characterize the efficiency, you could say, of these type of systems, energy is of course quite an important measure. Here you can see the power profile of the design nodes in a typical situation. So it's a typical duty cycle type of task that we can see the node is asleep for some period of time, wakes up and collects the sensor information, and then communicates the information wirelessly using LoRa radios before then going back to sleep. The total consumption is summarized up here of this active cycle. The energy consumption is about 200 microwatt hours, which basically provides us with months of battery life on typically sized batteries for this type of sensor node applications. What you can also see is, of course, that the LoRaWAN communication here is the main contributor to the energy consumption, both because it has high power levels, in this case over 300 milliwatt, as well as a quite long communication time of approximately 2 seconds. So the contribution of the LoRaWAN communication is more than 99% of the total energy consumed in one active cycle. And this is basically part of two reasons. One is that we use a quite high output power in our LoRaWAN radio, as well as a low data rate leading to long communication times, which both optimize for, you could say, a long communication range rather than a low power profile. To summarize some, or to exemplify some of the results that we can obtain and what kind of results you can get from this type of system, I show you here two examples, two example situations, a little bit in analogy to what you would think of as spectrogram, you could say, where we basically look at the output of our system over time. So basically look at the intensity and spectral information over time. So you can see on the top hand side here, we have a purely indoor condition with pure artificial light source, which basically shows us that we have over this 24-hour period a very stable intensity of about 402 lux in illumination, as well as if we look at the channels of our sensors, so basically the spectral information providing us red, green, blue, and infrared information, normalized over the intensity, which is also pretty stable over time. In contrast here, I have a situation where light source change over time, and this is due to that we have an artificial light source, as well as a window in the room that lets in some indirect sunlight at least. The window was so covered with a curtain. What we can see that the situation is quite different here. So in the beginning, we also here have a stable light intensity and stable spectral contributions. But as soon as the sun comes with a contribution, our intensity goes up, of course, quite significantly actually. But we can also see that our spectral contributions of the different channels have a change over time. Okay, to summarize our work and to conclude our work, we proposed a concept and a prototype application or implementation for distributed light measurements, including spectral information, or what we call for limited spectral information, as we do not collect the entire spectrum, but only a footprint of it. Our wireless system is a typical wireless sensor network, collecting all the data using LoRaWAN communication. And we hope that we showed that our design was quite energy efficient, which allows us for long operation times, as well as that we could observe through the data that we collected spatial and temporal spectrum changes. Motivating, of course, then that these systems are quite useful. Well, with this, I would like to thank you for listening to my talk, for showing interest in our paper. And of course, we hope that you will have a look at our paper and that you will contact us if you have any further questions. Thank you.